Assalamualaikum and greetings everyone. We are still on Stoke's theorem. According to Stoke's theorem, f dot dr integrate over closed curve C is equal to curl of f del cross f dot unit number vector integrate over open surface sigma. So sigma here is an open surface and C here is the closed curve, which is the boundary of the open surface. Alright, today I'm going to show you another example, which is question number 14C from tutorial 5. Okay, question number 14C from tutorial 5 says that we are asked to find we are asked to evaluate the surface integral by using the Stoke's theorem. So we are asked to evaluate the surface integral here, del cross f dot unit normal vector n over open surface sigma by using the Stoke's theorem, where f is given as this and sigma is the portion of the cone above the xy plane, so that the unit normal vector n points to the outside of the cone. Okay. Alright, so here I copied the question. It says f is given as this, and this is the open surface, which is the part of the cone that lies above the xy plane. So here you can see that we have minus square root of x squared plus y squared. So the cone is upside down cone, and then we shift 2 units up. Okay, let's sketch our cone here. Okay, so here we have the xy plane, sorry, xyz space. Okay, here we have the y-axis, x-axis, z-axis. Okay, so this is our surface, which is z equals 2 minus square root of x squared plus y squared. Okay, now when z is 0, what we have is 0 equals 2 minus square root of x squared plus y squared. Rewriting that, we get equals 2. Do some mathematical manipulation by squaring both sides, then we have a circle of radius 2. So let's say this is 2, this is 2, this is 2, and this is 2. We have a cone, okay, upside down cone. Let's say that's a 2. So it goes there. And when z is 0, we have a circle. So this is our open surface, 2, 2, negative 2. So that is our open surface, like that. Okay, all around. And it says unit normal vector n is points to the outside of the cone. So the unit normal vector would be pointing upwards, like that. Okay, so from the direction of our normal vector, we can get the direction or the orientation of our closed curve. So this is our closed curve. Our closed curve is a circle of radius 2 on the xy plane. So that is our closed curve C. And we want to know the orientation of our closed curve C. We use the right hand rule. So if the normal vector, so you put your thumb up, pointing upwards, then the direction of your fingers would be the orientation of the closed curve, meaning that the closed curve here is anti-clockwise direction. Okay, it's an anti-clockwise direction. Alright, now we need to evaluate del cross f dot unit normal vector over surface sigma by using the Stoke's theorem. So according to the Stoke's theorem, this is equal to, okay, let me show the Stoke's theorem again. So according to the Stoke's theorem, okay, it says del cross f dot unit normal vector n integral over surface sigma is equal to this line integral. So if we want to evaluate this by using Stoke's theorem, meaning that we have to evaluate the line integral. So what we need to calculate now is the line integral f dot dr over closed curve C. Okay, so we're not evaluating surface integral, but we're evaluating line integral. So it's back to the previous chapter. So this is going to be equal to, remember, f dot dr is the x component of the vector field f times dx plus the y component, z minus y dy, and the z component, x sine y dz over closed curve C. So this is what we need to evaluate, not the surface integral. So we need to evaluate the line integral. Okay, so we need the equation for our line for our curve, which is going to be a vector valued function. Okay, because we need to change everything in terms of t. So for our curve, we should have the x component, the y component, and also the z component. Okay, now if you look at our curve C, it is a circle on the xy plane. So on the xy plane, the z component is always 0. So from here straight away we can tell that the z component is 0. So we only need to find the x and the y component. So we want this in terms of parameter t and y in terms of parameter t. Okay, now when you I'm gonna sketch our circle here in 2D. If we sketch this in 2D, it's just a circle. Okay, let me sketch that. A circle of radius 2. So on the xy plane, we have a circle of radius 2. Here we have x, we have y, and we have a circle radius 2. So let's say that's a 2, and we have a 2 here as well. Okay, so that's a 2, negative 2, negative 2, and the orientation is anti-clockwise direction. Okay, the orientation is obtained from using the normal vector and the right hand rule. Okay, now we need to figure out the parametric equation for x and y using parameter t. Okay, now let's say here we have a point xy, remember from polar. So here the hypotenuse is 2, and let's say here we have a angle, let's call it t. Then we can see that cos t is adjacent, which is x, divided by hypotenuse, which is 2. From here we can tell that x is equal to 2 cos t. So now we have the parametric equation for x. And from the triangle there, sine t is opposite, divided by hypotenuse. So from here we get y is 2 sine t. So now we get the parametric equation for y. And of course z is 0. Okay, z is 0. So now we're gonna use this parametric equation for x, y, and z in our line integral here. Okay, but of course we need dx, dy, and dz in terms of dt. Okay, so if x is 2 cos t, then dx is equal to negative 2 sine t dt, and dy is equal to 2 cos t dt, and since z is 0, dz is 0 dt. Okay, so now we're going to change everything in terms of t. So in the first term we have tangent z, and z is 0, tangent 0 is 0. So from here we get this is 0. The second term we have z minus y. So we have z is 0, y is 2 sine t, and dy is 2 cos t dt. And then we have x plus sine y dz, but remember dz is 0, so again we have 0 there. And then from our circle here is we have a 1 hole orientation. So t is going to be from 0 to 2 pi. As you can see, when t is 0, x is going to be 2, and y is going to be 0. So we're here, and then one whole rotation, so t is from 0 to 2 pi. Okay, now simplify this. We get this is equal to -4 sine t cos t dt, t from 0 to 2 pi. And then you can use substitution, or you can use trigonometric identity. I'm going to use trigonometric identity, where we have sine 2t is equal to 2 sine t cos t. So from here we can write down sine t cos t, cos t as sine 2t over 2. Okay, so here we get -4, and sine t cos t is sine 2t over 2, and here we have dt from 0 to 2 pi. Okay, so here we get -2, and -4 divided by 2 is -2, and integrate sine 2t, we get and then we get integrate sine 2t, we get negative cos 2t over 2, and then replace t with 0 and 2 pi. Okay, so from here we get negative is positive. So here we have cos for pi, and then replace t with 0, we get cos 0. But we know cos 4 pi is 1, and cos 0 is 1. So from here we get this is equal to 0. So what we're calculating here is really work. F dot dr represent work. Okay, so if you want to evaluate surface integral using Stoke's theorem, then you have to evaluate F dot dr. But if you are asked to find F dot dr, which is line integral, using Stoke's theorem, then you have to evaluate surface integral. Okay, all right, that's it. Thank you.